So when we were last on this lecture on Wednesday, we were talking. We got to, I think, to get up to the right screen. We were just talking carefully about this example here, which I was leaving as an exercise. That these molecules are the same molecule, even though they're mirror. There's no mirror plane. There's no internal mirror plane. They are exactly the same molecule. So, what we need to discuss a little bit is we've sort of mentioned so far if something's an enantiomer or not. The alternative is if it is a superimposable mirror structure, it's the same thing. It's the same molecule. So if it's non-superimposable mirror image, it's an enantiomer. If the mirror images are superimposable, it means they're exactly the same thing because they are superimposable. Now, how do we define some of these terms? So a stereocenter is any atom at which the interchange of any two groups will provide you with a stereoisomer. And we're going to talk about what the class of stereoisomers are, and enantiomers are one of them. So I'm going to refine this because there are two different types of stereocenters. We're going to spend a lot of time talking about asymmetric carbons right now, or asymmetric nitrogens, because you can have those too. Any atom that can make 4 bonds makes a tetrahedron is asymmetric if it's got 4 different things attached. But carbons attached to double bonds are also stereocenters, although they're not asymmetric carbons. And that's because if you attach things at different positions on those carbons, they're not interchangeable. If I move the methyl group from here over to here, so if I just draw that structure, this one is that, top one is that something else, those are stereoisomers of one another. They're not enantiomers, they're not mirror images. But they're sort of double bond stereoisomers. There's not really a special term for them, we just call them stereoisomers. So the term stereocenter is more general. It's any carbon that can be involved in making a stereoisomer. An asymmetric carbon or an asymmetric nitrogen is an atom that has 4 different bonds to it. And I'm waving my hand around. You can't see me waving my hand around. Okay. So, with this lecture, we introduced the idea of chirality, molecules or objects with a non-superimposable mirror image, and chirality is a property of the entire molecule. We've discussed how to draw mirror images and how to try superimposing. We're going to get a little bit more practice in the next lecture, which we're going to start immediately. Asymmetric carbons are always stereocenters, but they might not always impart chirality to the molecule as a whole. And you can try playing around with mirror planes, but you have to be careful because sometimes they don't work. So a molecule that has, and I think I skimmed over this briefly, a molecule that has 2 asymmetric carbons. So let's say I have this molecule, and I'm just going to draw it similar to how we drew it earlier, or I can draw it like a normal person. Both carbon 1 and carbon 2 are asymmetric. Carbon 1 is attached to 4 different things. It's attached to a bromine. It's attached to a carbon that is attached to a bromine. It's attached to a carbon that is definitely not attached to any bromines. And it's attached to a hydrogen that we didn't draw in because it kind of crowds the structure and we assume that there are hydrogens there. So carbon 1 is attached to 4 different things. Carbon 2 is attached to 4 different things. The recordings for the lectures are on YouTube. It's in a syllabus. And they're both asymmetric, but there is an internal mirror plane. If I draw a mirror down the middle of the molecule, both sides of the molecule are identical. A carbon like a molecule like this, a molecule with asymmetric carbons, atoms. It's almost always carbons, but let's keep it more general. And in this course is always going to be carbons. I'm not going to, like, there was an example on the last slide with nitrogen, but it's always going to be carbons. That is not chiral. This molecule is not chiral because you can superimpose this mirror image on it. If you're not convinced, try it out. It's called a meso compound. I have no idea why it's called a meso compound. I don't know where the derivation of meso comes with that. But it means a compound that has asymmetric carbons but is not chiral. There are practice problems, and as soon as the assignment is done, okay, well, not as soon as the assignment's done because I've got better things to do on a midnight on a Friday, but tomorrow morning I'm posting at some ungodly early hour, I'm posting some practice assignments, and I'm probably just going to post over the weekend. I'm going to post like 6 or 7 practice assignments. They're not on Mobius, they're paper and pencil ones, and I'm going to post the answer keys as well. And if you don't know what to do on reading week and you want to do organic chemistry, you can get ahead of the course. You can catch up on some of the things that kind of cover some of the materials that we also looked at already. Are there cases where, so Casey says, when determining most acidic protons, are the cases where induction trumps resonance? It's theoretically possible. The induction, it's theoretically possible. I don't think we need to worry about examples like that. I think if you have a weird, yeah, I'm going to be posting not Mobius assignments or other types of assignments. They'll be on Blackboard. They'll be in a new resource folder. These are just sort of extra practice homework, like on top of textbook questions. And they're useful because, my exam questions are like that. Normally in the past, I would have drawn about half the exam from the assignments. I'm not going to do that this year because it's an open book exam. And so that really doesn't cover it. But I can say about half the exam is going to be very much like questions from the assignments. Okay. Yes, please keep everything. I guess I could download these ahead of time and get them all ready to go, but then I wouldn't have fun, like a little momentary break there. So we're going to sort of roll into even more stereochemistry. And we're going to talk about how to name stereocenters. So, and this is the R or S nomenclature. Just now in the chat window, is anyone ever seen the RS nomenclature before? Are there any yeses? Okay, okay. Heavy on the nose. Okay, we are going to go slower on this because this is really new for a lot of you guys. So we're going to spend quite a bit of time talking about that, because it's important actually. It's like the one-time naming is kind of important. And then we're going to examine how enantiomers have different physical properties. We're not really going to examine it in much detail. It's just I was trying to use different verbs. We're going to talk about the biological importance of enantiomers, and we are going to show how you can calculate the purity of a mixture of enantiomers. I am not going to ask you to do that math. It's silly, and you need to know how it's done theoretically. It's on MCATs. MCATs love stupid questions like this, but it's not really important. So we need to distinguish between different arrangements or configurations around asymmetric carbons. So if we have a molecule, this is alanine, is an amino acid. If we wanted to name it using like naming things, we would call it 2-amino-propanoic acid. Right? So carbon 1, carbon 2, carbon 3. That's going to be carbon 1 because that is your carboxylic acid. That is going to be carbon 3 because it is not your carboxylic acid. So you always start at the most oxidized end. And there's an amine on carbon 2. Sweet. Okay. This molecule over here is also 2-amino-propanoic acid. These molecules have a single asymmetric carbon. And if you have one asymmetric carbon, you are never a meso compound. Because we're going to get into a little bit of discussion about why, but it's impossible. If you have one asymmetric carbon, you have an enantiomer to that molecule. And so these are enantiomers of each other. They are non-superimposable mirror images. If you want, you can play around with this. And what you can try and do to prove that to yourself is rotate kind of around the axis, like the plane, so that the carboxylic acid, you try and superimpose this carboxylic acid onto that one with the same form. And what you'll find then when you do that is you'll have the hydrogen on top of the nitrogen, and you'll have this hydrogen on top of that nitrogen, and this nitrogen on top of that hydrogen. And you're kind of done. That's it. You can't fix it. They are non-superimposable mirror images. But they've got the same name if we use the naming system we've got so far. But they aren't the same molecule. So we have to have a way to distinguish between these two molecules. So what we use is what's called the Cann-Ingold Prelog convention. Each asymmetric carbon is assigned either an R or an S based on its 3D conformation. That's cool. But okay, it's not really that cool. But how do you go about doing that? So, assign a priority to each group bonded to the asymmetric carbon. And you assign priority based on atomic number. Sometimes it gets said based on atomic weight, but that's incorrect. It's atomic number because there's that weird place in the periodic table where you actually have a higher weight for a lower atomic number element. It's around gallium or something. So you assign based on atomic number. If you have different isotopes of the same element, then you default to weight. So iodine has a higher atomic number than bromine, is higher than chlorine, is higher than sulfur, blah, blah, blah. You got a periodic table, you can do that. So if we look at this, we look at this carbon here. Number 1 is your heaviest atom. I've got 4 atoms attached directly to this carbon, and all I'm looking at is the atoms directly attached to the carbon. I'm not looking at the molecular weight of the group. Like, obviously, a CH3 is heavier than an NH. Well, it's the same weight. They're actually all about the same weight. But if these were longer chains, I wouldn't be looking at that. I'm only looking directly at what atom is attached to that carbon. And the atom that is attached to this carbon is a fluorine, a carbon, a nitrogen, and a hydrogen. Well, hydrogen's easy. It's the lightest. Hydrogen's always the lightest. You can't get lighter than hydrogen. The first thing I should actually check is to make sure I've got 4 different things attached. And here I kind of do. It's pretty clear. The heaviest one on the periodic table is fluorine, so fluorine is 1. The second heaviest is nitrogen. The third heaviest is carbon. Cool. I can write numbers. That's good. Now what you have to do, hopefully, I got this on the next slide. Nope. So I might come back to this in a second. I'm going to walk through a few slides, and I'm going to be surprised by what I find. In case of a tie, like this guy here, in really horrible resolution, I'm really sorry about that. This carbon is attached to 3 different carbons. Well, those are all carbons. That doesn't help me very much. Okay. So what I look at next is, well, what's the heaviest thing that carbon's attached to? Well, this carbon is attached to another carbon. That's good. This carbon is attached to another carbon. That's good. This carbon is attached to another carbon. That's good. We're still tied. Okay. We're going to go back to our first atom in that chain, and we'll go, okay, what's the second heaviest thing it's attached to? Okay, the second heaviest thing this guy's attached to is a hydrogen. The second heaviest thing this guy is attached to is a hydrogen. The second heaviest thing this guy is attached to is another carbon because it's got 2 methyl groups on it. We have a winner. This guy is the heaviest because that carbon, the first atom that's attached to this, is attached to something heavier. But we still have a tie for second place. So what's the third heaviest thing this guy's attached to? It's another hydrogen. And this guy is also another hydrogen. We are tied. And we have run out of atoms attached to that carbon. So what we go down to is the next heaviest thing attached to that carbon. Well, now we're going to walk over to start looking at these carbons. Because we have exhausted the atom previous, and we've chosen the carbon over the hydrogen because carbon is heavier than hydrogen. We're going down the heavier possible chain here. So this carbon, the heaviest thing it's attached to is a bromine. This carbon, the heaviest thing it's attached to is a hydrogen. Clearly number 2, it's attached to heavier things. Higher atomic number things. I'm saying heavier, but I mean higher atomic number. They're almost always the same. And I'm not going to mess with you with stupid galliums. So like atomic weight, atomic number, doesn't matter. Definition is number, but weight will get you there as well. And this one's number 3, which leaves this pathetic, like the 4 looks like it's over here, but the 4 is attached to this pathetic little hydrogen here because hydrogen is light. So the hydrogen's the last thing, right? It's obvious that central carbon. So really good question, Mariam. The hydrogen finishes last. We've got these 3 big, ginormous, hulking wrestlers, and we've got me, and I'm the hydrogen, and I am definitely in 4th place on that one. Okay. What if you have something stupid like a double bond? Well, let's say we had this molecule. I'm just going to change the color of my pen. So again, let's just quickly go, okay, we're attached to 4 different things. Do a quick investigation on the molecule. Make sure you're attached to 4 different things. Otherwise, you're wasting your time doing this, right? The hydrogen is obviously number 4. Phew. Okay. Then we're attached to 3 carbons, and we're tied again. We can go down one more chain. Every single one of those blue carbons I've just dotted is attached to another carbon. So they remain tied up to there. We can't easily break it. Then we start getting something interesting because this is a double bond, and how do you take that into account? And the rule we take that into account is we say, okay, we're going to attach it to a ghost carbon that isn't attached to anything else. They're just ghost carbons. They're not real carbons. They're not attached to any other atoms. But for counting purposes, they're attached to a second carbon. So if we're starting to look at this then, this carbon here, I'm going to call it carbon A. I don't want to use number B and D because C stands for carbon. B stands for boron, but there's no borons around here, so it's not confusing. Or not that confusing. So carbon A is attached to a carbon and then to another carbon. Carbon D is attached to a carbon and then another carbon. Carbon B is attached to a carbon and then a hydrogen. So carbon B is eliminated. It's voted off the island, and it is number 3. Which leaves us with carbon A and carbon D in a cage match. And of course, what we have to do here is now the final thing that these are both attached to is they both have hydrogens on them. Those are real hydrogens. It's a tie. Okay, so now we need to go down this thing. So what's the heaviest thing this carbon D is attached to? Well, it's either one of these carbons, and they're the same, so it doesn't matter. Just go to this guy. I'm going to take a look at this carbon. What's the heaviest thing it's attached to? Again, not going backwards. I don't count going backwards because we already know that's all a tie. The heaviest thing it's attached to is a hydrogen. What's the heaviest thing this carbon is attached to? It's that ghost carbon. And so this guy wins. And so when we assign the priorities, we come up with this. Okay. Great, we've written numbers on a page. Now what do I do with those numbers? So what we do is once you've assigned the priorities, you rotate them such that the fourth priority thing, almost always a hydrogen, is pointing directly away from you. You gotta do this rotation in your head, or you can build a model kit and do your rotation with your model kit. So we're gonna point the lowest priority thing directly away from us, and then it basically looks like we have a fan pointing or a propeller. It's got 3 things. It's almost like it's almost like those Newman projections we were drawing earlier. When we were looking at butane conformations, we had 3 things 120 degrees from each other. And what we're basically going to figure out, in this case, at this point you don't need to draw anything except numbers. And I go, are those numbers clockwise or counterclockwise with respect to each other? I'm really bad at clockwise and counterclockwise and left and right. And so besides being a disaster when I'm driving with my wife and she's giving me directions, it does make doing this difficult for me. So I need to really think about this. This is clockwise. And this makes this an R enantiomer. This other enantiomer is anti-clockwise or counterclockwise. I don't think anti-clockwise is a word. Should be. Shorter right than counter. So it's the S enantiomer. And that is completely freaking arbitrary. But it is what it is. So we can try this with a few things. So let's have an example here. Oh, I don't know. Say we have this molecule. I don't know, take 30 seconds, try and assign the priorities, and then determine whether when you stick the little group back, you have an R or an S. Should we have a stopwatch? This lecture, like everything I do, is brought to you by Pepsi. Should really ask for a sponsorship deal. Okay. I finally changed color on my pen. So again, just try and make our life easy. The hydrogen is number 4. It's always the lightest. The fluorine is heavier than carbons because we know we have 2 carbons attached. And so the fluorine is number 1. then we have 2 carbons, and we're going to run into this constantly. It's very normal. You have lots of carbons attached to things, and they tie. So when we look at, okay, what is the heaviest thing this thing is attached to? Well, it's another carbon. What's the heaviest thing this thing's attached to? Well, it's another carbon. What's the second heaviest thing this thing's attached to? Well, it's a hydrogen. What's the second heaviest thing this thing's attached to? It's a carbon. So it's going to be number 2. It's going to be number 3. There is an OH that's hanging there, and oxygen's heavier than carbon, and you're really tempted to try and walk your way over to it, but you never get to it. It never gets involved in the calculation because you break the tie before you get to that oxygen. Okay, great. It's not oriented right. So I'm going to show you 2 ways to approach this problem. The first way is you are a genius in 3-dimensional thinking, and you go, this is easy. What I'm really seeing is that. To be honest, this isn't the most difficult rotation to do. So in this case here, I've drawn a propeller such that I got 2 things kind of pointing out towards me. I'm rotating along that fluorine carbon axis and just sort of swinging the carbons out towards me and putting a hydrogen back and away from me. And now I know that that's 1, 2, 3. I go around the circle. It's clockwise. That is R. Okay. Let's say you're not good at that, because most of us suck at it. I can draw a tetrahedron with it in the pane, so that's fine. That would be Quinn. That's complete. So Quinn, I should read the question. Quinn said, shouldn't the current with the OH be aligned with the plane of the page and so not have a bolded line? Yeah, that's absolutely, you can do that. That's kind of like if the angles are like this and you have 2 lines in your plane of your page, but you can kind of swing it a little bit so it's coming out towards you a bit. It's completely arbitrary that I did that. I just did that to stick the hydrogen straight back and away from me, in which case both the other guys are kind of coming out towards me a little bit, like my arms. Like my head and my arms are kind of the bonds, and I guess my back is the other hydrogen pointing towards the hydrogen bond. It would be completely correct to draw it in the page. But let's just draw the numbers. So we're just going to draw the stereochemistry in the numbers. And I'm going to do a couple of things here to sort of show you why what I'm doing is okay to do. So I'm going to draw the mirror image of this. Okay. Now, if I rotate this mirror image 180 degrees, I can get 1 and 4 lined up just like on the, you know what, I'm going to just change the color here. I'm just going to recolor this guy. Just because I'm going to call him green and red or something. Oh, I'm really sorry. I just realized I have someone who's red-green colorblind. Okay, the one I just drew there, I can't remember who it is who's red-green colorblind, but if you're red-green colorblind, the one on the left is green. Okay, so this red one, I can get the 1 and the 4 overlapping, but what I'll have is I'll have the 3 pointing out towards us and the 2 going back and away. So these are not the same molecule. But if I physically rip off atoms 2 and 3 and I swap them, this is not chemistry. This doesn't happen, but it's useful for us. then I'm the same as the green. So what I've just done is I've switched two of the groups around. I've swapped their positions. Like it's a trade, right? It's a 1-for-1 trade. No draft picks. And you make the same molecule. Okay. When you think about that for a second, that makes perfect sense. Enantiomers are mirror images of each other. There's only ever, for one asymmetric carbon, there's only one other way it can be done. Like there's 4 atoms, there's 2 ways to arrange them in space. There's the R and the S. You switch any 2 atoms on R, you make S. You switch any 2 atoms on S, you make R. That's kind of how it goes. So where the hell am I going with this and why does this matter? Okay, let's say you really suck at rotations. What you really want is you want 3 on the back. You want 4 on the back. And so what you can do is you take this guy and we're going to swap 3 and 4. So without having to do a rotation, we have swapped 3 and 4. Now 4 is going directly back and away from me. And now I look and I go, oh, okay. That looks like it's S. It's counterclockwise, which means that must have been R because I swapped 2 groups. So because I did a switch, I've changed it from one to the other. It will work every single time as long as you keep track of how many switches you make. And this way you don't need to rotate your molecule. I don't really like giving like sort of these kind of hint, I don't know what to call it, a trick or a hint or something, because most of the time they're not universal. They work some of the time and not others of the time. I'm happy to share this one because it works every single freaking time. Like it is just a fundamental nature of the material. So, that's why this will work every time for you. So if you have trouble with rotations, this can be a nice little shortcut. You are still going to need to rotate the molecule for other things, but you're not going to need to do it for this. You just need to keep track in your head about how many times you've rotated these switch groups. But at the same time, you're keeping track in your head how you're rotating things. So depending on who you are, one of those might be more difficult than the other. Okay. So if we're looking at physical properties of enantiomers are pretty freaking similar. So remember a few, last lecture, I think we had fumaric acid, maleic acid. It was like 100-degree difference in the boiling point or melting point or some point. Here, what we're noticing is that they're all absolutely identical. I don't think this is relevant. I think this is from a previous textbook. They have the same, 2 enantiomers have the same boiling point, they have the same melting point, they have the same refractive index, they have the same density, they have the same freaking everything. They are identical physically. Except they rotate plane polarized light in the opposite direction. This is pretty simple. You take a light source, you beam it through a monochromatic filter. Today you would use a laser and skip this step and you would have a laser. You pass it through a polarizing filter. So light's going in you have all different vectors. You have thin slits, so only light aligned in a certain direction can go through. And then you pass it through a cell containing your material dissolved. And if you have one enantiomer, it is going to bend the light because the light interacts with it. I do not understand this at all. I don't know how this works. It's basically this just freaking magic. And then you can actually see that the light bends it one way or the other. And you can measure this using a protractor, or you can measure it using a computer, which is how anyone sane does this anymore. You get sort of a reading out saying this is the angle. If the cell contains chiral molecules and an imbalance of chiral molecules, then it will rotate the light. If it contains an equivalent amount of R and S of one molecule, they'll cancel each other out. The R will pull it over by a certain angle, the S will pull it over by the opposite angle, and they'll cancel out to 0. For a long time, enantiomers were thought to be these kind of things that did this, because that's where it really mattered. And we're going to see why it really matters, because nobody cares about this. This really isn't very important. But it's the old school way of thinking about how to determine the purity, enantiomeric purity of something. So dextrorotatory was termed D or plus. So that's a molecule that rotates light to the right. Levorotatory is termed L or minus, rotates to the left. This has absolutely nothing to do with RRS. Some R molecules are dextrorotatory, some S molecules are levorotatory. There's actually no way to predict for a molecule whether it's going to be dextrorotatory or levorotatory for a given enantiomer. We do not have a physical model for how this works. We do not understand why molecules bend light this way. So there's probably a Nobel Prize in physics waiting for somebody who figures this out. We do this math where we say, look, the specific rotation is how much your sample is rotating light. The observed rotation is, this, I want to make sure I get this right. Okay, so this is for an enantiomerically pure sample. When you only have one enantiomer, this is correct. It gives you this parameter called specific rotation. This is corrected for when you observe the rotation of your sample, and you divide it by the concentration of your sample and the length of your sample in decimeters. You can tell how old this is because they're using decimeters as a unit. Who does that? So what we're looking at here, and grams per milliliter, we would always use moles today. So these are very, very old measurements. What we're looking at here is kind of controlling for concentration and length. And of course, depending on what solvent it is, it matters. So if you're doing this in water versus doing this in ethanol, you're going to get a different specific rotation. So you need to define what your solvent is as well. But you can kind of correct for these kind of terms. So if you have a slightly different instrument and yours is 10 centimeters long and mine's 11 centimeters long, we can still talk with each other. This really isn't very interesting. So again, highlighting there is no connection between R and S and plus and minus. You can have R dextrorotatory and S dextrorotatory. Where it really matters isn't with plain polarized light. Nobody cares about plain polarized light. What we really, really, really care about is this stuff, the biological properties of enantiomers. This is super important. So chiral molecules, stereoisomers, occupy different places in space. And now when they're just interacting with each other, boiling points, blah, 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 it's symmetrical. It doesn't matter. You have all one thing, and then like the universe is the mirror image universe, and it's fine. The problem is our proteins are made up of chiral molecules. So our proteins are chiral. And that means they interact with one enantiomer of a molecule, and they interact differently with another enantiomer. I really want to find, I'm going to have to make a better image of this because I can't find one online. But, this is a very crude idea of how an enzyme can work. So you can see we have an enzyme. It is a green blob. It has 3 paler green blobs in it, which are basically places where parts of molecules can fit. So this top green blob is designed to only fit this catechol moiety, this diol thingy, this 2-hydroxylbenzene thingy. This thingy isn't going to fit anywhere else. This molecule can only fit this pocket down here because it's designed to fit it. Notice it's slightly negatively charged. That's good because this is positively charged. It all makes sense. Nice stereo electrostatic interactions. Everybody's happy. And then there's a little pocket over here, which is slightly positively charged, and sure, oxygen can interact with that. That's nice. Then we have the hydrogen sticking out away from us, and that's cool because that backside is a wall, and the hydrogen can't stick into the wall. We're kind of screwed if we're using the enantiomer of this molecule because we try and lock this guy in. The hydrogen's got to stick out away towards us. but now we're trying to put this thing into the wrong pocket and this thing into the wrong pocket. It doesn't fit and it doesn't go in, and a protein doesn't interact with this thing. And so this is why one enantiomer of epinephrine does this, and the other enantiomer of epinephrine does not interact with this protein. So it matters a lot which enantiomer you have when you're making a drug, because drugs interact with proteins, and proteins are chiral. So you often need a chiral molecule. So what's really, really cool is our nasal smell receptors. There's been a lot of work in the last 20 years actually on this. So I'm not up to date at all on everything that we understand about how the nose works. But your nose smells the difference between two enantiomers. So this is carvone. The S enantiomer is a natural product. It's found in nature. It's extracted from caraway seeds, and it smells like caraway. So it's a nice rye smell. Minus carvone smells like spearmint. Those are two different smells. The only difference is the arrangement of the atoms in space. So what's that telling you, of course, is that your nose has got some protein receptor, which is interacting with either R or S, and then signaling to your brain that one smells like mint and one smells like caraway. And it just blows my mind that we have like proteins that, first of all, we have a protein to smell mint and caraway. Like, that seems kind of wasteful. And we can tell the difference. It's always mattered, and the big story where chirality suddenly became a huge deal, and often it gets told that this is where it started to matter. No, it mattered before this. We always knew it was there. It's just normally, it's really cheap to make a molecule, both mirror images of the molecule, and shoot it into you. And we know that 50% of it's going to work and 50% of it's going to do nothing because it's not going to interact with anything. Of course, thalidomide is the example where 50% of it works really, really well to quench morning sickness, and 50% of it causes damage to fetuses, leading to birth defects. So that was bad. There were a lot of lawsuits, quite rightly so. And now we learn more and better, and we always provide a single enantiomer. One of the big risks with this, of course, was that you can never really test a drug. We don't test drugs on pregnant people. And so it was really hard to kind of figure out if this would cause birth defects because we didn't test drugs on pregnant people. And when you test on pregnant rats, there are no birth defects. But that's because rats are a lot more selective than humans. And so when a rat fetus is actually growing up defective in any way, the mother rat actually kills the fetus internally and then reabsorbs all the tissue. And so there's not even like a trace that it was defective. So rat models do not work very well if you're looking for birth defects. So you kind of need to use humans, but you can't use humans because that's not unethical. So you're kind of in a really big problem, and there's no really good solution to this thing. Anyways, thalidomide was banned for about 30 years. It's now back on the market. You can actually get thalidomide again. It's under a completely different brand name, and it still works really, really well for motion sickness and morning sickness, except we only use the one enantiomer, and we're not using it for morning sickness, and it's not for pregnant people, but it works really, really well for people who are undergoing cancer treatment and can't stop getting sick, can't stop vomiting. And it works. It's the best antiemetic we've got. So if you have equal amounts of two enantiomers present, exactly equal amounts, you have what's called a racemic mixture. And that gives you an observed optical rotation of 0, because half of it's pulling it one way, half of it's pulling the other. They cancel each other out. You get 0. That mixture can also be called a racemate if you don't want to write a bigger word like racemic mixture, or 2 words. So if you take an equal amount of S2 butanol and R2 butanol, you get an optical rotation of 0. That's pretty neat. Okay, no, it's still not neat. The biology stuff is neat. So how do you get racemic mixtures? You get them because you react a non-chiral starting material with a non-chiral reagent, or an achiral starting material with an achiral reagent. There's no chirality anywhere in here. There's no selectivity. So we're going to talk about this reaction. Actually, we're not going to talk about this reaction in the course at all. But you can add hydrogen across a ketone. So you add one H to one carbon and H to the oxygen. And it can equally add from the top face of the ketone. So it's interacting with the p orbitals of the carbon and the oxygen. We're going to get into a discussion on that because we're going to do other chemistry with these kinds of things. And if you attack from the top, you get the R because the hydrogen's on top. If you attack from the bottom, you get the S because the hydrogen's on the bottom. And it's a 50-50 shot. There is no difference in the energies leading to either of those. It has an equal chance of doing both. Now, if you only had 10 molecules that you were doing this to, the chances that you would have 5 and 5 is pretty low. You'd probably have like a non-equal amount. But we're not doing it to 10 molecules. Like 1 mole is 10 to the 23 molecules, which is a lot of molecules. And so if we're doing it to 10 to the 23 molecules, the chances that you'll have 1 times 10 to the 23 and 1 times 10 to the 23 on both sides, you're not going to be off by orders of magnitude. You might be off by a bit, but it's random. So you're more or less have the same amount of both. And by more or less, I mean within statistical error that you can't measure, you have the same amount of both. And so you get an equal amount of both materials. If you have an unequal mixture, you can actually measure the optical purity by dividing your observed rotation by the rotation of the pure enantiomer. We then use a term which I really despise. You are going to come across it, so I have to teach it, called enantiomeric excess, which you define the excess of one over the other minus over the entire mixture. So what do I mean by that? So if I had 8 molecules of R and I have 2 molecules of S, I have 10 total molecules. Okay, great. And I have, basically what's happening here is 2 molecules of R cancel out 2 molecules of S. So 2 molecules of R pull to the left, 2 molecules of S pull to the right, they cancel each other out. Now I've got 6 molecules of R pulling to the left. And so it looks like you're going to get 60% of the expected rotation. So if normally I rotated by 100 degrees for pure R, if I rotate by 60 degrees only, then I've got a 60% enantiomeric excess. I know that I'm getting 60% of that total rotation. This is really confusing. I hate this. I'm not going to ask you to do this math. You are going to come across it in other courses and in other, well, you're going to come across it. If you do the MCAT, you will come across it because they love this stuff. So we can do this math. You got 6 grams, 4 grams. You can convert that to the number of moles, but it's all going to be ratios, right? So who cares? We'll just stick with numbers. So again, you got 10 as your denominator because that's 6 plus 4. You got 6 minus 4. That equals 2. So 2 over 10. So that is 20% enantiomeric excess. So as I said, this is a stupid way to do this. The way we generally do this now, and the reason we do this is because this was when you only had polarimetry, you only had this plain polarized light to do measurements. You had no other way to do it. Now, of course, we use something much better called enantiomeric ratio, which is I've got 6 grams of one, 4 grams of the other, and so I have a 6-to-4 ratio. Or 3-to-2, right, if I reduce that. I'm not talking about these excesses, I'm not doing these subtractions, I'm just saying, look, I've got 3R to 2S. And it's because we use different techniques now to measure enantiomeric excess. And ratios are a lot easier than doing the subtraction, where you have to kind of keep track of the total, and it's confusing. Like, there's a reason it was there, it was because that's how we got to it, but now we don't use that anymore. Okay, so we're at 2:21. I'm going to call it a day right here. Somebody has a question. Going to So Fatima, that was the whole point why we. I'm sorry. That was the whole point why we had the practice assignments to practice using this kind of thing, so you could practice trying to run through the questions and see and make sure you didn't make that mistake. There's no labs next week. Yeah, no. Unfortunately, these things are baked in. That is the assignment. Obviously, your practice assignment is going to replace this one because you're not going to get a good mark on this. Like we can't replan them for people like this. This is sort of an evaluation. No, you. No, I can't actually authorize that. Like I can't actually go in and make that happen. Like I don't have that ability to do that. And so it does count as the assignment. I'm really sorry. Like I emphasized that a bunch of times in there. I'm really sorry. Like that's why I highlighted that you have to be really careful with this, and that's why I wanted people to be able to practice with it. I think the grades will be available. What we have to do is we have to export all the Mobius grades, upload them up into Blackboard. I think you'll be able to see them on Mobius. You'll be able to see how you did on Saturday morning. So Saturday morning, as soon as the exam ends, as soon as the assignment ends, you'll be able to go in and take a look and play around with it and take a look at your grades, see what questions you got right, what questions you got wrong. But you can only get that feedback once the assignment's over. So I think you'll be able to see your grade there. Your grades will then be downloaded from Mobius by the GAs, and we'll be uploading them to Blackboard. And we have to do that manually because the two programs don't talk to one another. So we have to be very careful with how we input those. I I know. Um, I I'm sorry, Fatima. Like I don't know what to say. Like I said, be very careful not to push the wrong button. You push the wrong button. I don't know what else to say. Like I highlighted that was a major risk, and I know a lot of people did that by accident. Yeah, this is it. It's the assignment. It's kind of like what you did is you walked up to me, handed me your exam. So you kind of handed it in, and I can't hand the exam back to you. Like it's a formal evaluation, and I'm sorry about that. If you did. I'm sure you did the practice assignment, and hopefully that went smoothly, and you'll be okay.